Good morning, everyone, and welcome to our presentation. We are Group 18. Our project is the Santander Value Prediction Challenge. Santander Group is a Spanish multinational commercial bank and financial service company. Based on industry research, the customer retaining rate is 80% if a business provides personalized service. Therefore, Santander's goal for this challenge is to go a step beyond recognizing that there is a need to provide a customer a financial service and intends to determine the amount or value of the customer's transaction. This means anticipating customers' needs in a more concrete but also simple and personal way. With so many choices for financial services, this need is greater now than ever before. To summarize it, the objective of this project is to identify the transaction value of each potential customer. The metric to be used is going to be measured in minimizing the root mean squared logarithmic error. And the link for the Kaggle competition is right on the screen. The data provided by the Santander Group has already been split into the train and test set. The train data has 4,459 rows and 4,993 columns, which include the target in the second column. The test data is much larger with 49,342 rows and 4,992 columns, omitting the target column. The first column of both data sets is customer ID. There is also a sample submission file to illustrate desired output formatting. Just two columns, customer ID and target, meaning transaction value. Scanning through the data sets, all the columns' names are anonymized, and the values are all numerical, but with a lot of zeros, so quite sparse. Now we're going to take a look at two notebooks that helped us shape our own notebook. The first notebook we are going to look at is the Extra Trees Minimal Starter Notebook. It is coded in Python using a regression tree approach. It scored 1.5 in private leaderboard and a little higher in the public leaderboard. Basically, we can see that this solution is very simple compared to other solutions, especially the winning solution, but presents our team with a starting point for how we can possibly improve upon or even run with this type of model. The data is partitioned, a regressor tree algorithm is applied, and few parameters are applied to arrive at a result. However, a result is produced with very few lines. This regression tree model uses min-samples leaf, the argument, that indicates the number of samples at a leaf node. It is set to 2 right now, which is quite low for predictive accuracy. And there's no cross-validation to prune the trees. To improve upon it, we can use the boosting model that has small sample points to sequentially build trees. And the boosting model will allow us to tune more parameters to customize learning. In addition, there's minimal data exploration, which we can see from other notebooks, which is key because some data cleaning and feature engineering within the sparse context of our data allows for improved results. The second notebook that we looked at is called An Idiot's Guide to a Not Horrible Score Notebook. And this is published by Thomas Melson. It is a XGBoost model in Python that scored a little higher than the previous one. The code is very short as well. After loading and splitting the data, it just got rid of features that had no variance, aka the columns with all the same values. Then the data are fitted into an XGBoost regressor at default with setting the 300 estimators. Finally, they exponentiated the results and submitted. This model, also like the first one, does not do any exploratory data analysis to inspect the dataset first. Also, to tackle the many feature problem, it only simply removed columns with no variance. So, the possible area of the improvement is adding EDA and building a more sophisticated feature selection scheme, such as selecting features based on importance or selecting features that has RMSE below a certain threshold. After looking at other well-performing models from the competition, it is obvious that the best solutions came from an XG boosting model that used some feature cleaning and engineering in order to get better results. We were able to use what we learned in addition to insights from notebooks in order to construct a model that takes into account initial data analysis, many more parameters, cross-validation, and advanced skills that were introduced in some of the better solutions within the competition. As I mentioned, the model that we will be using in our notebook is the XGBoost model. We did not cover this in our machine learning class. However, it is based on the original boosting model. As we know, trees are able to build classification models and regression models, and we know that boosting sequentially builds trees. XGBoost is based off boosting. However, it is even more advanced because it has more hyperparameters and allows us to avoid overfitting and bias in some other ways. So now I'm going to jump into our code. We do have a GitHub page where you can look at it more in depth, but I'm going to go over the main sections and look at some of the output that we have in order to summarize our findings. Initially, we read in our data, and we used some functions to clean up some of the sparsity that we had in our data. So as I mentioned, we had some duplicates, we had some highly correlated variables, and we got rid of some of the zeros. Next, we see that there are a lot of parameters that we can play around with in the XGBoost model. We take advantage of that here. A lot of the parameters are reliant on others, therefore they were dictated by some of the values that we have. Here, we create a train and a test and cross-validate, and then make predictions as well. As I mentioned, we made 3 functions earlier, and we now use that on the train set in order to clean up our data set. That's under the cleaning data section. In our model construction section, we use the function from before, the get underscore XGB, and the cross-validated results, and we iterate through them, and then we will see that this for loop is able to print out different results for the best cross-validated results for our predicted function. So as you can see here, it kept iterating until it found a close enough predicted value. Next, we take into account different metrics that will allow us to predict our key metric for the Kaggle competition here. In addition, we set up our test X, test Y, train X, and train Y in order to put into our final model. You can see here that once we finally plug in a new set of parameters and our train set in order to create our final model, it keeps running through sequentially until it reaches a certain threshold and finds a sufficient result. This final parameter right here dictates how far this will run until it finds an optimal iteration. We also graph the importance here. I do not show it because we didn't use too much of the importance to identify which model we would build. However, we did take into account the parameters and did play around with that in terms of creating our optimal model. Ultimately, we wrote this to a CSV with the original format where we had the ID in the first column and the target in the second column. As you can see here, our final RMSLE is 1.365. That's an improvement on the first and second notebook that we analyzed. It's in the correct format, as I mentioned, and we have the correct length in terms of how many predictions we wanted to make. So we can see that the XGBoost model here was cool to play around with in terms of all of the different parameters it offers. And it was also a success in terms of looking at a lot of different ways that the parameters can adjust the result and come into terms with getting a better outcome than some of the other notebooks. So that is our presentation. Thank you.